This video is on linear momentum and impulse. Question 1. Use Newton's third law of motion to complete the next sentence. Man throws rock forward. So that's the action. The reaction is rock throws man backwards. Question 2. What is the meaning and equation for impulse J? Do not confuse impulse J with current I. So F equals ma, which is equal to m delta v over delta t, which is equal to m v final minus v initial over delta t. Let's multiply both sides by delta t. So F delta t equals m times v final minus v initial equals mv final minus mv initial. This term here, mv, let's just let it equal p. Okay, p equals mv, and p is the momentum of the object. So F delta t equals mv final minus mv initial equals delta p. So F delta t equals delta p, we'll just call this equals j. J is the impulse of the object. Impulse is the change in momentum of the object. So impulse is j, it's equal to delta p, which is equal to F delta t. Question 3. What is the meaning, symbol, equation, and fundamental units for momentum p? Momentum is also called inertia in motion. Why? Do not confuse momentum p with pressure p or power p or density rho. So momentum is inertia in motion. Momentum is directly proportional to the mass and velocity of the object. If the mass and or velocity of an object increases, then it is more difficult to make that object speed up, slow down, or change direction, or accelerate. Previously, inertia was directly proportional to mass only. So P equals mv has units of kilograms, meters over second, or newtons. Times seconds. Newton seconds. So for example, stopping a bullet fired from a gun requires a large force because of its large velocity. So if V is big, P is big. So it requires a large force to stop that. Here's another example. Stopping a slow-moving train requires a large force because of its large mass. Since M is big, P is big. And since P is big, it requires a great force to get that object to stop. Question 4. Why are the front of cars built so weak? Why are cars so easy to damage during an accident? So imagine being in a car accident where the car stops completely. Take a look at this equation. So this is the equation from problem 2. If we want V final to be 0, we want the car to stop safely. So we have this equation. So for safety reasons, we need F to be as small as possible and delta T to be as long or large as possible. This is why the front of cars are built weak, and this is why we wear seat belts, because we want the time to slow down and stop to be big. So the force that we feel is incredibly small. Question 3. Why do athletes have their elbows bent when catching a ball? Why do athletes have their knees bent when coming down after jumping? We need to maximize the time to stop an object to minimize the force acting on our body for safety. So take a look at this equation again. If we have V final to be 0, the left-hand side is F delta T, the right-hand side is minus mv initial. So for safety reasons, we want delta T to be as big or large or long as possible. So the F that we feel, the force, is a push or a pull. So the force we feel is going to be as small as possible. Question 6. What common mistake do people make when firing or shooting a gun? So, Newton's third law of motion. Bullet moves forward, gun moves backward. So shooters must hold the gun tightly when firing. So many times people do not hold the gun very tightly. So please do watch this video on YouTube. It's quite funny. Question 7. What does the law of conservation of momentum tell us? What is the equation for the law of conservation of momentum? Memorize this law because it comes up a lot in multiple choice questions and free response questions. If there's no external forces in an isolated system, then momentum is conserved in a collision or explosion. P initial equals P final. Question 8. What is an elastic collision? Is momentum conserved? Is kinetic energy conserved? Is total energy conserved? So this is a definition you have to memorize. In an elastic collision, kinetic energy is not lost in a collision. So momentum is always conserved, so energy is always conserved, but the kinetic energy is not conserved. Question 9. What is an inelastic collision? Is momentum conserved? Is kinetic energy conserved? Is total energy conserved? In an inelastic collision, momentum is conserved because it always is. Total energy is conserved because it always is. Initial kinetic energy is not equal to final kinetic energy. So this is true. So compare the difference between elastic collision and inelastic collision. Remember, collision is when two objects hit each other. Question 10. What is a perfectly inelastic collision? Is momentum conserved? Is kinetic energy conserved? Is total energy conserved? In a perfectly inelastic collision, two or more objects collide and stick together. In this case, we have the most kinetic energy lost in the collision. So momentum is conserved because it's always conserved. Total energy is conserved because it's always conserved. Kinetic energy is not conserved. Question 11. What does the area under a force versus time graph tell us? The units is Newton's second, which is the same as impulse. So this means that the area under a force versus time graph tells us the change in momentum of the object. Question 12. What does the slope of a line on a force versus time graph tell us? It has units of kilograms, meters over seconds cubed, which is something we're not familiar with. It tells us that the slope of a force versus time graph tells us nothing. Question 13. A 2-kilogram block is moving east with a speed of 5 and hits a wall and rebounds to the west at a speed of 4. What is the magnitude and direction of the change in momentum of the block? First thing you should do is draw an image. Always draw an image. I chose positive x to go to the right. I could have chose positive x to go to the left, but I just chose it to go to the right. So if you want, do this problem again, but just make positive x go to the left. So it's asking for the change in momentum. So just look at mv final minus mv initial. This is mv final. V final is -4. This is mv initial. V initial is +5. This is our solution. There's a negative sign. That negative sign means to the left. Why? Because in the image, going to the right is positive, or east. Going to the left is negative, or west. Question 14. A 2 kilogram block is moving east on a frictionless surface with a speed of 5. It then moves on a rough surface for 3 seconds. Finally, it continues to move east on a frictionless surface with a new speed of 1. What is the force of friction on the rough surface? So when we draw this image, we notice that the object slows down on that brown surface. So let's just use this equation. Say positive x is to the right or east. V final is 1 meters per second. V initial is 5 meters per second. And the time is 3 seconds. It was on that brown surface for 3 seconds. So solve for F. So F equals minus 2.67. So the negative sign means that the force is to the west. So I said positive x is east or to the right. Question 15. A force versus time graph is shown below for a mass being pushed in a horizontal line. Part A, calculate the magnitude of the impulse given to the mass. So the area under the curve gives us the impulse given to the mass. So let's just determine the area under the curve, and that's delta P, or F delta T. Part B, calculate the average force given to the mass. Well, if we look at the image, there was a force versus time graph for 7 seconds. So that's why we're dividing by 7 seconds. Question 16. Abroad, the aircraft carrier Carl Vinson, a steam catapult exerts a force of 800,000 newtons on a 24,000 kilogram F-14 Tomcat. Find the time for the kitty to accelerate from rest to 65 meters per second. So we were given all the values. Let's just solve for delta T. Question 17. Each minute, a snow cannon shoots 150 snowballs, each having a mass of 0.08 kilograms. In the barrel, the snowballs are accelerated from rest to 475 meters per second. Find the force exerted on the snowballs. So, we're given all the information. The most tricky part would probably be delta T, because we need that in seconds per snowball. Question 18. A pump accelerates oil whose density is 850 kilograms per meters cubed from rest to 5 meters per second. The volumetric flow rate through the pump is 0.4 meters cubed per second. Find the force exerted on the fluid. So remember, mass is density times volume. In the front of this equation, we have mass. So substitute density times volume. And we have volume in the numerator, delta T in the denominator. So just group that together, which is meters cubed per second. And we were given the volumetric flow rate in meters cubed per second. And we could obtain the solution. Question 19. A baseball which has a mass of 0.685 kilograms is moving with a velocity of 38 meters per second to the right when it contacts the baseball bat, during which time the velocity of the ball becomes 57 meters per second in the opposite direction. Part A, how much impulse has been delivered to the ball by the bat? So draw an image so you understand what's happening. And make sure you get your directions correct for V initial and V final. So in one moment it's going, let's just say to the right, yes, and the next moment is going to the left. So if I say to the left is negative, I get negative 57 meters per second minus 38 meters per second. That's going to be my delta V. Part B, while in contact with the bat, the ball undergoes a maximum compression of 1 centimeter. Approximately how long did it take for the ball to be stopped by the bat? So we could use a Suvat equation to determine the acceleration. Then we could use another Suvat equation to determine the time it takes for the bat to hit the ball. So once we have delta t, we have our answer. How long did it take for the ball to be stopped by the bat? Remember, V final is going to be 0. Okay, V final is 0 because it says stopped by the bat. Part C, what would be the average force applied to the ball by the bat while stopping the ball? See, it says while stopping the ball. That means V final is 0. And the time we obtained was from part B. Question 20. A rocket has a mass of 49,000 kilograms and is sitting at rest in space. It contains 186,000 kilograms of fuel. When this fuel is burned, it is exhausted from the rocket with a velocity of 38,500 meters per second to the left. For simplicity, assume that all the fuel is emitted at once. What will be the final velocity of the rocket? So let the right be the positive x direction, and let's let the fuel be exhausted to the left, because that's given to us. So this is the law of conservation of momentum. The total momentum in the beginning equals the total momentum in the end. So draw two images. First, the rocket at rest, that's the initial image. The final image is the rocket going to the right and the gas is going to the left. So the rocket and the gas is M1V1. The rocket by itself going to the right is going to be M1V1 final. And the gas and the velocity of the gas is going to be M2V2 final. So understand, the initial M1V1 is the rocket by itself, not moving with the gas in it. M1V1 final is the gas going to the left, and M1V1 final is a rocket going to the right. M2V2 final is a gas going to the left. Solving for V1 final, we get this velocity. That means the rocket goes to the right. Question 21. A 3 kilogram block is moving west at 4 meters per second on a frictionless horizontal surface. A 5 kilogram block is moving east at 6 meters per second on the same horizontal surface. Both of them collide and stick together. What is the final speed and direction of the block? So draw an initial image and a final image. So if you read the problem, initially we have two objects, and final we have one object because it sticks together, both objects. I said positive x is to the right. So initially we have two objects, that's P1 plus P2. At the end we have one object, that's P final. Plug in for everything, our final velocity is 2.25 meters per second. That means after both objects hit, they go to the right together at 2.25 meters per second. Part B, is momentum conserved? Yes, because it's always conserved. Part C, what's the original total kinetic energy? Find the total kinetic energy of both objects before they hit and add them up. Part D, what's the final total kinetic energy? Find the kinetic energy of the object after they hit and stick together. So is kinetic energy conserved? No, it's not conserved because kinetic energy initial does not equal kinetic energy final. So this is a perfectly inelastic collision. Part F, is this an elastic or inelastic collision? It's a perfectly inelastic collision. Part G is total energy conserved. Yes, it's conserved because it's always conserved. Law of conservation of energy. The lost kinetic energy is transferred to deformation, heat, or sound. Question 22. A 7 kilogram block is moving north at 8 meters per second on a frictionless horizontal surface. A 9 kilogram block is moving south at 10 meters per second on the same surface. They collide. The 7 kilogram block is now moving south at 4 meters per second. So draw an image. Draw an initial and a final. And why don't you also label a positive x or positive y axis? I said positive y is north. So part A, what is the final speed and direction of the 9 kilogram block? We're going to use a law of conservation of momentum. Initially, we have two objects. So on the left-hand side, we have P1 initial plus P2 initial. Finally, we have two objects. We have P1 final plus P2 final. Plug in, we were given everything except V2 final. Make sure you get the positive velocities and negative velocities correct. We could solve for V2 final. So I get a negative sign, which means south, because I said north is positive. Part B, is momentum conserved? Yes, because it's always conserved. Part C, what's the original total kinetic energy? We're going to use this equation. Remember, for kinetic energy, V is speed, so we don't care about the positive sign or negative sign. And since we square the value, the negative sign goes away anyways. Part D, what's the final total kinetic energy? You could see what was done there. Part E, is kinetic energy conserved? No, because the solution for part C is different from the solution from part D. So this is an inelastic collision. Is this an elastic or inelastic collision? Part F asks. This is an inelastic collision. Part G, is total energy conserved? It's conserved because energy is always conserved. The lost kinetic energy is transferred to deformation, heat, or sound. Question 23. A 12 kilogram block is initially at rest on a frictionless horizontal surface. It then explodes into 3 pieces. So a 3 kilogram block moves west at 4 meters per second. A 5 kilogram block moves east at 6 meters per second. What's the final speed and direction of the 4 kilogram block? So draw an image. I drew an image. I drew an initial and a final image. And I said positive x is to the right. So P initial, I only have one object. Once it explodes, after it explodes, now I have 3 objects. So now let's solve for V3 final. So V3 final, I get minus 4.50 meters per second. The negative means the object is moving west. Is momentum conserved? Part B, yes, because we have the law of conservation of momentum. It's always conserved. Part C and D asks for the initial and final total kinetic energy of the system. Part E is asking, is kinetic energy conserved? And the answer, no, because our solution for C and D are different. Part F is asking if total energy is conserved, and the answer is yes, because energy is always conserved. Question 24. A 12 kilogram block is moving east at 13 meters per second on a frictionless horizontal surface. It then explodes into 3 pieces. A 4 kilogram object moves east at 5 meters per second. A 6 kilogram object moves, a 4 kilogram object moves west at 5 meters per second. A 6 kilogram object moves east at 7 meters per second. So part A, what is the final speed and direction of a 2 kilogram block? So let's draw an image, an initial and final. And we're going to use a law of conservation of momentum. Initial situation equals final situation. Initially we had one object, finally we had three objects. We know P equals mv. So let's just solve for V3 final. We get we get positive 67 meters per second. The positive means east, because on my image I said positive is to the right or east. Part B, is momentum conserved? Yes, because we have the law of conservation of momentum. It's always conserved. Part C, what's the initial total kinetic energy? Well, it's our initial situation. We have only one object. So it's this equation here. Part D, what's the final total kinetic energy? We have three objects at the end. So we're going to use this equation. Part E, is kinetic energy conserved? No, because parts C and D are not equal to each other. Is total energy conserved? Yes, it's always conserved because it's a law of conservation of energy. Question 25. A rifle which has a mass of 5.5 kilograms is used to fire a bullet which has a mass of 65 grams at a ballistics pendulum. The ballistics pendulum consists of a block of wood which has a mass of 5 kilograms attached to a string which is 125 centimeters long. When the block is struck by the bullet, the block swings backward until the angle between the ballistics pendulum and the vertical reaches a maximum angle of 38 degrees. So when this pendulum swings backward, it means it goes up to the right, according to this image, 38 degrees. Part A, what will be the maximum gravitational potential energy contained in the ballistics pendulum when it reaches the maximum height? So let's just say at the beginning, this pendulum has a height equals 0. How high does it go up after the bullet hits the pendulum and the pendulum goes up? Delta H is equal to this equation. 1.25 minus 1.25 cosine 38 degrees. So we get mg delta H, and our answer is 13.2 joules. Part B, what was the velocity of the block of wood immediately after being struck by the bullet? So, law of conservation of energy. So we have the kinetic energy of the bullet plus the block on the left side equals the total gravitational potential energy when the block reaches the top on the right side, and just solve for velocity of block plus wood, which is 2.28 meters per second. Part C, what was the velocity of the bullet immediately before it strikes the block of wood? So now we're going to use a law of conservation of momentum. See, part B was a law of conservation of energy, part C is a law of conservation of momentum. So in part C, we have the bullet going to the right and the wooden block at rest. That's this side here, before they collide with each other, before the bullet collides with the wood. And on the right side, we have the bullet and the wood colliding with each other. Let's solve for the velocity of the bullet. And we get 178 meters per second approximately. Part D, how much work was done by the bullet as it lodged in the block of wood? It's 1/2 m bullet velocity bullet squared, about 1030 joules. Because work is equal to the change in kinetic energy. Part E, what would be the recoil velocity of the rifle? Remember, bullet goes forward, rifle goes backward. So in the beginning, the mass of the rifle and the bullet was 0 when they were together. In the end, the bullet goes to the right and the rifle goes to the left. So let's solve for velocity of the rifle. It's negative 2.10 meters per second. That means the rifle goes to the left. Part F, how much energy was released when the bullet was fired? This is going to be the kinetic energy of the bullet plus the kinetic energy of the rifle. Because remember, in the beginning, the kinetic energy is 0. Because the bullet is in the rifle and it's not moving. I know there was a lot to learn in this, but take these problems one at a time. You'll understand everything, hopefully.